All right, so this is going to be the last talk of this session by Louis, who is actually, as well, a PhD student at LAAS-CNRS. But as you know, you are like a bit original, but because you're co-hosted by IRT Saint-Exupery, which is close from here. I don't know if you know the B52 building. Yeah, it's famous in Toulouse. You're going to talk about a presentation titled Attack Scenarios and Embedded Intrusion Detection for Space Systems.
Yeah.
Thank you.
Thanks for the introduction. So I'm Lolive. I'm going to talk about embedded intrusion detection in space systems. This work was funded by the IRT Saint-Exupery CSS project, so cybersecurity for space systems. So the aim of this project, you can see we have the following partners. The aim of this project is to simulate and detect cyber attacks on a satellite constellation. And we are located here in Toulouse. So to give a bit of context, satellites are strategic assets. They are used in communications, GPS, etc. And they can be target of cyber attacks. So, for example, there was a Viasat attack at the start of the war in Ukraine, which targeted a constellation used by the Ukrainian military. There also was the Obstat demo hack by Thales, or there was the Hackersat competition, which targeted satellites. So, as of now, there are no or very poor embedded security mechanisms, and we need strategies to improve the security. So, there is obviously the security by design that should be considered when designing a product, but we will focus here on the intrusion detection aspect. And of course, there are some space context challenges, such as limited resources. Those are critical systems. We also have periods of autonomy, meaning we cannot always communicate with the ground. And there are specific protocols. So for the embedded intrusion detection, there are quite some papers in the state of the art. Mostly, we can group these methods in AI-based methods, which are often based on anomaly detection, and non-AI methods, such as state automata, heuristics, etc. And in the case of satellites, existing works are only theoretical, and or are based on non-specific hardware or attacks. So, for example, there is a paper on the CAN bus, and the attacks are CAN bus specific attacks, meaning they are really close to attacks that we can see in vehicles, and not specific at all to the satellite context. So now, if we look at the constraints that we have to deal with, concerning regarding the datasets, the existing datasets only have ground data of the satellites, so commands and telemetry received from the ground, and there are no datasets with internal bus data. So it's quite incompatible with on-bus detection approaches. We also have computing constraints, such as limited CPU and RAM, and no human onboard intervention is possible on a satellite. So this led us to design a signature and heuristic-based detection. So to give a quick overview, some of you may already know, but satellites, when we want to execute an action on a satellite, we send a telecommand, and the satellite sends down telemetry, which is the data from the sensors, etc. So for our threat model, we are focusing on attacks that are impacting the satellite, so they need to be detectable on board. For example, data exfiltration on ground is not considered at all. And attacks can come from two main threat vectors, so it can be either a ground station, legitimate ground station compromise, or satellite payload compromised, but we assume that the payload of the satellite is safe. The platform, sorry, is safe. So the attacks can use one or more telecommands, and we consider multiple attacks, such as network flooding, system crash, etc. And our detection has to adapt to the diversity of the attacks. So we do not have a real satellite at hand, so we used a simulation environment, which is based on NASA's NOSCUBE CubeSat simulator, and it is a specific fork developed in the CSS project. It uses well-known CCSDS, so Consultative Committee for Space Data Systems communication protocols, such as the Space Packet Protocol and telecommands. And it has a software bus architecture with every application connected on a single software bus. So, as you can see, there is a ground segment which communicates with our space segment via telecommands and telemetry. And in the satellite, the entry point is the inter-satellite link. So it receives the packets. Then the packets are forwarded to the command ingest component, which is in charge of the deciphering of the packets. And then they are forwarded on the software bus and forwarded to every application which subscribed to the specific packet. And in this simulator, the RF layer is not present at all. And the payload of the satellite is a camera for Earth observation. So, for the attacks that are considered, we are considering network flooding, application kill, file swipe, satellite spin, etc. So a whole range of attacks. And as you can see, most of these attacks are sent either from the ground or from the embedded payload. And that is because the attacks that we consider are network attacks, so the packets can be sent either from the ground or from a payload on board, a malicious payload sending packets on the bus. So for the ground attacks, the tool that we developed is named the input generator, and it is used to send command using the correct space packet syntax. And we can use it, we did use it for ground attacks, but also for legitimate traffic. And for the payload attacks, we edited the payload, so the camera code, and we considered that these attacks can be present either before launch or loaded during updates of the payload. So, just a quick overview, but not every attack is as easy to detect. For example, network flooding, where you have a really huge amount of packets in a really short period of time, is easy to detect, whereas application spoofing or behavior deviation of the payload is really hard to detect. And so now that we have discussed the attacks, we want to establish some detection strategies. And so the first that we will do is on packet arrival. So we consider that we have encrypted traffic, but the header and the trailer are in plain text. We can verify the inter-packet times. We can verify the integrity of the packet as well, verify the correctness of the header or the packet size. And if we look after the decryption step, we now have access to the command content, and we can analyze the dangerousness of the command and establish a whitelist of commands usually sent from the ground. And finally, where we are located on the bus and look at the internal packets, we can do an analysis of the dangerousness of the internal commands and establish a whitelist of commands per application. And this is a future work, but we plan to use AI to detect payload deviations. So now that we have looked at the strategies, how do we implement them in our environment? We put these strategies matching the probe's location. So for example, we will put the first probe in the entry point, so the inter-satellite link component. The second probe will be located in the command ingest component, which is in charge of the deciphering. And the last one on the software bus. And these probes will collect data that will be fed to the detection algorithms that I will present later. So for the first probe, we want to, we are before decryption, and we want to address the following attacker behaviors. So for example, flooding of commands from the ground. We have an anti-flooding module. We want to address jamming or malformed packets. For this, we have a CRC verification module. Malformed packets, but with a correct CRC, we have a packet size verification module if we are in block cipher. And if we have incorrect header values, which are, for example, used in the cryptolib crash attack of the literature, we use verification of the header. So those are simple but efficient heuristics. And now, if we are after decryption, we have access to the packet contents, and this enables us to detect even more developed attacker behaviors, such as correctly formed but dangerous single commands. And for this, we will use a module that I will present later, which is named the THC analyzer, in stateless mode. And now, if we want to look at correctly formed but dangerous command sequences, we will use this same module but in state machine mode. And we will also look at slow flooding of packets using the same command with a slow flooding module. So this access to packet content enables a rule-based approach. And finally, on the last probe, we are located on the internal bus. We can access the internal packets. And the behaviors that we are targeting are an internal application sending unauthorized commands. So this will be taken care of by the application profiling and, to some extent, the THC analyzer. Dangerous commands or sequence received, again, we will use the THC analyzer module. And a payload which would deviate from its normal behavior, we could use in future work anomaly detection. So this access to internal exchange also enable a least privilege approach, as well as a rules-based approach again. So I've teased it a bit to present this THC analyzer module. It's globally similar to a firewall with top-down rule processing. So the first match is the rule which will be processed. It has internal state machines. We can drop packets or raise alerts. And it has a flex Python parsing. And we have two instances, one on probe 2 and one on probe 3, with different rule sets, because some attacks are only detectable on the internal bus, but for those who are detectable earlier, we want to detect them as early as we can. And so if we have an incoming packet, it will go through all the rules, and if there is no match, we assume that it is a legitimate packet, but if at some point there was a match, it is a suspicious or malicious packet, and we have to execute the corresponding action. So for the rules that apply to the THC analyzer, we have syntax, which is composed of current state, which will be used in stateful mode, an action, which is either switch to a state, raise an alert, or drop a packet, and command identification fields, as well as parameter characteristics, and finally the parameter values that we will match on. So for the state-readiness rules, packets are inspected independently, and we are targeting one-shot attacks. So those are attacks that can harm the satellite with a single command. For example, there is the system file swipe attack. So with this delete all command, which wipes a folder, if you use it on the /cf folder, which contains the configuration files, we can erase a lot of necessary files in the satellite. And to prevent this, we will use the following rule. So D for drop, the IDs corresponding to the delete all command, string type, and the /cf value. There is also another attack in the literature, which is the cyber attack, which uses the stop app command, which stops an application without restarting it. And if it is used on the command ingest applications, then packets incoming from the ground can no longer be processed, and so the satellite is completely isolated. So to prevent this, we will use the following rule as well. So now, for the stateful rules, we want to be able to detect a malicious sequence of commands. And so this is possible with state machines that are fully customizable. And they use, under the hood, a deterministic finite automaton. So, for example, if we have the app deletion attack, we delete a file, application file, we stop the application file, and then the application can no longer be restarted ever again. But if a file is received right after the file deletion, it corresponds to an update and not to an attack. So we have to take that into account, and this gives us the following state machine. With the state 0, if we receive a delete, switch to state 1. If we are in state 1 and receive a stop app on CAM, we block the packet. And if we receive another file again, we go back to state 0. This is legitimate. And this translates to the following rule with every rule at the end of each other. So now that we designed our IDS, we wanted to evaluate it. And we first evaluated the detection accuracy. So we didn't observe any false positives except for a specific case, which was for the anti-flooding heuristic when there is a file transfer. This is because in our current simulator, file transfer is made via UDP style, so transferring as fast as we can. And this can resemble a lot network flooding. So we implemented something to provide to disable this anti-flooding during file transfer. Except from that, no false positives, and all attacks were detected, which proves that our approach is relevant, even though when we start from the attacks, this is to be expected. And then we decided to evaluate the net resources consumption of our IDS. So we had two experimental setups. The first is with the current rule set, which allows to detect all the attacks that I've mentioned. And it is around 20-ish rules. And another one with 1,000 rules to evaluate the scalability of the approach. And we did not see any significant impact on CPU, but there was an impact on RAM usage. For example, with the 20-ish rules, there is very, very few RAM used, but for the 1,000 rules setup, we are almost at 132 kilobytes of RAM used, which can become quite significant for resource-constrained environments such as satellites. But this number of 1,000 rules was chosen to be voluntarily extreme and is quite unrealistic in our opinion. For the latency part, you can see quite huge increase in percentage, but we have to take into account that on the software bus, there are around 100 messages per second, and so an increase of 20-ish microseconds is negligible compared to those 100 messages per second. So overall, we have a low impact, and we have an impact on memory when we are utilizing many memory rules. So this IDS is satisfactory as of now, but it could be improved. For example, we could correlate information with state variables of the satellites or ephemerides, so the position of the satellites on the Earth. We could also specify conditions or ranges in the detection rules. And we are also exploring complementary approaches such as anomaly detection on payload behavior or satellite bus with data sets that we are actually generating as of now. And also correlation with an angle probe, which could enable to determine attack location or give detailed information for operators. Thank you for your attention.
Thank you, Louis. I'm all alone for question, but I can run.
Thanks. How do you generate the rules for the applications, which are, as I understand, provided by somebody else? And to make sure that they don't... You mentioned a whitelist of rules for commands. How do you generate that?
Okay, so the whitelist of commands used per application on the bus is established empirically, looking at all the commands that are used in a legitimate use case over long simulations as of now. It could be improved to be spec-based. If you know the spec of your satellite, you could have a very specific and more accurate list for this command.
Thank you for your presentation. I've heard that on satellites, computers are doubled, redundant. Is it possible to try to confuse those twin systems?
I think, yeah, it can be double, but on some use cases, on our use case, we are on a CubeSat simulator. On CubeSats, it's not always doubled, so we don't have this problem as of now. It could be a problem for sure, but if those systems are communicating via a network bus, we could maybe use our approach to some extent to implement rules on those behaviors. And if not, I think you would have to design a specific module for this aspect.
Thank you for the presentation. I was wondering, is it possible to detect an intrusion based on the source that is sending telecommunication? Because I don't know how many satellites, how many ground stations are sending messages to the satellite, and is the ground station authenticated?
Usually, there is authentication and encryption, or there should be. If there is not, you probably are going to encounter trouble in the following years. So yeah, usually the ground station is authenticated, and you could determine that a certain ground station is sending illegitimate commands. But as we consider that the ground station that we communicate with can have been compromised, that's in a way our hypothesis at the start. But if we use an on-ground probe, you could, for example, say my on-ground probe didn't see this packet coming, so an attacker must be sending commands to my satellite directly with its own antenna. Or on the other hand, I have seen this packet on ground, so this particular ground station may be compromised.
Thank you for the talk. I'm not the expert in satellite, but in real world in IT, signature-based doesn't work because it's so easy to escape them with obfuscation, etc. Can we do some obfuscation, for example, in satellite?
I don't know if you can do obfuscation directly on the common payloads, but you could always add a command in between the signatures that we modeled in our state machines and find a way to do the same attack, but in a different sequence and evade our detection. So this is why we are trying to consider anomaly detection to have a better understanding of the legitimate behavior of the satellites and able to be able to detect attacks that we may not know, but we should have to be able to do that. We should have a really good accuracy.
Thank you.
Okay, so we are going to stop here.
All right.
Thanks a lot again. Till the break.
Yep. Yes.
Just
so we want to maintain a bit of coffee break, so we are going to resume.